I'm Ramirez, and I am the lead for Group 3, and the experiment we are going to be doing is conduction. So the objective of this experiment, we are going to estimate the time required for our aluminum plate to reach thermal equilibrium. We're going to determine the steady state or temperature field throughout the plate, and then we are going to numerically predict the temperature field evolution using a conventional implicit finite difference algorithm, and then we're going to compare our results from what we predicted in our experiment. So what is conduction? Conduction is a form of heat transfer through a non-moving material. What happens is if you heat up part of a material, the molecules inside of it start to vibrate the more heat gets put in, and then those molecules hit other ones, which transfer that energy, heating up those, and it just continues as it transfers along. So the apparatus we're going to be using is this one right here. We have a aluminum plate, and inside these little dots are our ports where we're going to be measuring the individual temperatures. We have 2 heaters, 2 ice baths, and the rest of the apparatus is covered with insulation for an adiabatic wall. So the procedure that we're going to be doing is we're first going to measure the initial temperature of the plate, and then we're going to clamp the hose for the ice bath and fill that up with ice and water. We want to make sure that there's no water on the top of the aluminum plate because that'll mess with our temperatures. We want to adjust the rheostat so that there's a 200 watt combined power. We do have 2 heaters, so we want 100 on one and 100 on the other. Then we're going to place a thermocouple in the center of the plate and measure the time for it to reach thermal equilibrium. And then once we reach thermal equilibrium, we're going to measure the individual ports and their temperatures so we can get the temperature of the overall plate. So the math behind this is we have a plate right here, and so we're going to assume that the surface 1 is instantly heated to temperature TWI, and the surface 2, which is the top one, is instantly heated by a uniform heat flux of Q2, and then surface 3 and 4 are both adiabatically insulated, so their heat is going to be 0. From that we get a thermal energy equation, which we're going to start with, which is the partial derivative of temperature over, with respect to time, which equals the thermal diffusivity times our second order partial derivative of temperature with respect to x plus y, or with respect to y. So to solve for that, we need an initial condition and we need 2 boundary conditions. So our initial condition is basically just saying that at T equals 0, we have a temperature of T naught. And our boundary conditions, so at the surface 1, we have our initial condition is TWI, and then at surface 2, we have a heat flux of Q2, and then at surface 3 and 4, we have heat of 0. So now we need to discretize the spatial domain for the plate, and by doing this, we need to find delta x and delta y, so we take the width of the plate divided by the number of total grid points minus 1. So for our specific apparatus, we have a 7-inch long width, and we're going to divide that by the 8 grid points that are along it minus 1, which gives us 1, and then do the same thing for delta y, which also gives us 1. So if we choose delta y and delta x to be the same number, it makes our calculations a lot easier. So the approximations for the derivatives, just for the second order partial derivatives of temperature with respect to x and y, this is what we get here. And then we are going to use the alternating direction implicit method, or ADI, which divides the time integration into 2 steps, and we'll plug in our partial derivatives into over here. And this K is the time level. So we're going to be increasing our delta T at a time rate. And so K is just an integer of 1 to a certain number. So now setting delta X and delta Y equal to each other, we get this right here, where our lambda is alpha times delta t over delta x squared. And looking at our ports near the boundary, we're just plugging it back into this equation here. So those around the boundary are GO cells. And so those are it's not really considered because it lies outside of the computational grid. So we have to solve those individually. And so we can find that by using this equation right here, where K is our thermal conductivity. It's not the time stuff anymore. And then that's going to be for surface 4, so it's going to equal 0. So from there we can find the temperature for that GO cell. And it can be used for all ports located near that boundary. So we can put this into a matrix form and be able to solve it using linear algebra. So what can we expect? So, just common sense, it's going to be a lot hotter near the heaters and colder near the ice baths, but you're going to get a nice equilibrium point right around the middle of that aluminum plate. Any questions?
Can you connect this experiment to some physical process or what is the use of doing this experiment?
The use of this?
Where do you see such conditions? Any physical process that you can point out to?
I guess we just did the experiment with the air conditioning, so you could probably use the same thing. You've got the heater from, the sun coming in from the window, and then the ice bath could be sort of like the air conditioning. You can measure how that temperature is distributed across the room. I guess it's different because this is 2